Dear students, today we will discuss about the motion of rockets. We know that rockets are used to place artificial satellites in their orbit. And the motion of rockets, the working of rockets, is simply based on the principle of conservation of linear momentum. Now, suppose I have a rocket of mass m, which is projected with an initial velocity v. Therefore, what is the initial momentum? P1, it is mv. Remember, m is the total mass of the rocket. When we say a rocket, it means the container as well as the fuel that is inside it. So the sum total of the two is this m, total mass of the rocket, and the initial momentum is mv. V is the velocity with which we have initially projected this rocket. Now, as the rocket begins to advance, begins to move, we know that its velocity increases. That's quite obvious. Velocity increases, and because it is losing fuel in the form of gases, so its mass decreases. That's also very obvious. The velocity with which the gases leave the chamber, leave the container, is called as exhaust velocity, denoted by VE. Right? So if we have to write the final momentum at any stage of the movement of the rocket, we can write that final momentum P2 is m minus delta m, because now this rocket has lost certain mass in the form of these exhaust gases, and the velocity is enhanced v plus delta v. To this, we will also add a factor delta m times v plus ve, where delta m is the mass of the gases that leave the rocket. In fact, when they leave in the backward direction, they produce a thrust on the rocket in the forward direction, due to which it progresses ahead. Right? Now, v is the velocity, and ve is the exhaust velocity with which the gases leave the rocket. Now, the very first question that you can ask me straightway is that the direction of v and ve is opposite, so we should give minus sign to one of them, and that's quite obvious, that's quite right, but we'll take care of that sign in future. Right? We'll take care of that. So for the moment, let us carry forth the derivation in this manner. Obviously, what I want to say is that indeed this v, the velocity with which the rocket is moving ahead, is in a direction opposite to the exhaust velocity of the gases. So we'll take care of this negative sign, but in certain steps from now. Now, what is the total change in the momentum? The total change in momentum is how much? P2 minus P1. So that is given by delta P. So what is that? Delta P. For that, we'll first try to simplify this P2. So write this P2. What is it? It is mv plus m delta v minus delta m v minus delta m delta v plus v times delta m plus ve times delta m. So both these quantities are very small, delta m and delta v. Their product will further be a small quantity, so it is neglected. This term is neglected. Now what about this v delta m plus and minus? This also cancels. So we are left with P2 is equal to mv plus m delta v plus ve delta m. And what is the change in momentum that we are interested in? That is P2 minus P1. So we have found P2, that is mv plus m delta v plus ve times delta m minus P1, and that is simply mv minus mv. So this and this will go, and delta P is how much? It is m delta v plus ve times delta m. Now, if we differentiate this expression throughout by time, what do we get? We get dp by dt is equal to m times dv by dt plus ve times dm by dt. Now, let us carry forth it on the next page. So we have obtained that dp by dt is equal to m times dv by dt plus ve dm by dt. Now, this is the external force. So we'll replace it by Fe. So this Fe is m dv by dt plus Ve times dm by dt. We can also choose to rewrite it by keeping m dv by dt here and rewriting it as Fe minus Ve dm by dt. Now, as all of you understand that the rocket keeps on losing the mass at every time, so this dm by dt is intrinsically a negative quantity. So it is intrinsically negative. So for this dm by dt, we give a sign from here that it is negative. So once we do that, this m dv by dt is equal to Fe plus Ve times dm by dt, because we have replaced dm by dt by minus times dm by dt, because we know that this rocket is losing the mass on account of exhaust gases with every passing moment, right? Now, this is actually the final equation with respect to which you can describe the motion of the rocket at every stage. See, this is the net force acting on the rocket. This is the thrust. This term, this factor is called as thrust. And why do we call it thrust? Because this is the force that is due to the exhaust gases. Because they are moving in the backward direction, they are producing an equal thrust on the rocket to move in the forward direction. And this is the thrust on the rocket due to the gases that leave from behind, right? So that's why we call this factor as thrust. This is also a force, but we call it thrust more properly. And this is called as external force. This external force can be interpreted in two ways. One is that as long as the rocket is within the reach of gravitational force of Earth, so as long as it is moving within gravitational force, this Fe will be mg, simply the weight, right? But once this rocket advances, moves ahead and surpasses the gravitational field of Earth, we know this Fe is 0. So beyond the gravitational force, gravitational field of Earth, this Fe would be how much? 0. But within the reach of gravitational field of Earth, this Fe is how much? mg. So to write it more properly, we say that it is m dv by dt is equal to minus times mg, because now we'll take proper care of everything. Because the weight is always acting downwards, we will also give them a negative sign. And also remember that we have not so far given the negative sign to this VE, because VE is also acting in the backward direction. So we'll write minus VE dm by dt. And to be more particular, we can choose to write that this is ma, net acceleration, is equal to minus mg minus VE dm by dt. And this is the final and the most proper equation which takes care of all quantities together with the sign, together with whatever sign is suited to them. So for all numerical problems, you can choose this equation. Now we have to do some more manipulations to it. That is, when we are moving, obviously when we want to launch a satellite, we have to surpass certain regions. So when we are moving in such region in space where there is no gravitational field of Earth, this quantity will be 0, and we are left with what? We are left with m dv by dt is only equal to this much, Ve times dm by dt. Ve times dm by dt. Now let's carry forth the discussion from here. If we see that dt and dt virtually cancel, right? So we are left with integral. We can simultaneously choose to integrate dv 1 by Ve is equal to integral dm by m. So obviously this will be integral. Sorry, my pen is not working. So this will be integral dv. Do I have to carry forth with a pencil? I guess so. So it is integral dv, right, is equal to ve times integral dm by m. So let us choose this integration from some initial value v naught to some final value v. Similarly, from the initial value of the mass of the rocket to some final value mf. So this will be v minus v naught, and this will be ve times log of m final by log m initial. I hope you understand that. So if the initial velocity, if the rocket begins its motion by at rest, for example, we say that we have chosen to fire the rocket from the position of rest. So for the sake of simplicity, we say that initial velocity is 0. So we put v naught equal to 0 and v is equal to ve times log of mf by mi. So the final velocity vf is given by this expression. Now I can ask you to use these equations to solve certain numerical problems. For example, I may ask you to find the rocket speed. Find the rocket speed when this ratio, that is m naught by m, is equal to e square. This is the initial and this is the final mass of the rocket. If the ratio of the two is e square, what is the final velocity? Final velocity, you can make use of this equation, right? So v is equal to ve log of m naught by m final by m initial, right? So it's like this. So if you also give negative sign to ve, then it is v times minus ve log of m by m naught. So here you can choose to give the value directly, that is e square. 2 will come down. In this case, you can write it as v is equal to ve log of, because it is written that this is equal to e square. And remember, this is to the base e. So 2 will come down, log e will be 1. So velocity of the rocket will be twice ve if the ratio of the initial and final masses of the rocket are e square. Remember, whenever we talk about the final most mass of the rocket, that is essentially the mass of container, because at that time all the fuel inside the rocket has been burnt out, and this final velocity is also called the burnt out velocity of rocket, and the rocket at that time is essentially left with only the mass of the container. So I hope these sets of equations help you in understanding the basics, the preliminaries of the equations of rocket. I hope you have understood it well. So that's all.